The first one is Dr. Enrique Garcia, who is CTO, Chief Technical Officer of the National Composites Centre in the Bristol, UK, who will be delivering his talk on the D4C, Digital for Composites.
So hi, I'm Enrique Garcia, as I was introduced, and I'm going to talk about digital for composites. So first of all, thank you for the organizers to actually inviting me and giving us the opportunity to talk about this. So for those of you who don't know the National Composites Centre, we are part of the High Value Manufacturing Catapult, which is part of the Catapult network. We're 7 different centers, each one of us with a different specialty. Of course, ours is composite materials. The entire Catapult, but also for the NCC, our mission is basically bridging the valley of death. So the focus of the NCC and the rest of the Catapult centers is around this applied research, so mid-TRL. So we work quite closely together with the academics, especially in the UK, all of them working within SimComp. I think Michael Wisdom will probably introduce you to some of the stuff that has been happening there and also in Bristol. And we also work really closely with industry. So more and more, we're doing more effort in transferring the applied research into real industrial applications and then allowing the industry to actually take on those technologies. The National Composites in a nutshell, we were open in 2011. A lot of different equipment. I will give you a glimpse on some of the stuff that we have been doing in the past. 2 different facilities, around 350 composite engineers at the NCC, but also Axis, now being called the Bristol Composites Institute. There's another 150 engineers and researchers there. So quite a lot of composite knowledge, real critical mass around composite design and manufacturing in Bristol. So I'm not going to focus on the kind of equipment that we have, but well, as you can see, we have very different scales. I would say that probably the NCC, one of the key aspects or key technologies that we have developed is automated deposition. Quite a lot of different technologies, as you can see. And again, we can move from very small composite parts all the way up to a full-scale wing. And we are actually developing and manufacturing together with Airbus a full-scale wing. We also have braiding and quite a lot of high volume technologies like the one that you see below, the overmolder. Also paying a lot of attention to inspection. And that is, as I will mention later, not only final inspection, but also in-process monitoring. I won't dwell too much on this, but as the previous presenter has already mentioned, sustainable composites is getting more and more important. So we have quite a lot of different initiatives that are all encompassed into one single program that we call SASCOM. And essentially what we're doing is looking at both aspects. So on the one hand, is there any way of developing new materials that are more sustainable from the beginnings, biomaterials, for example, but also is there a better way of taking full advantage of some of the materials that have already been manufactured? So with that idea, this is a technology that was developed in Bristol, at the University of Bristol. And now we are collaborating with the University of Bristol in making sure that this ends up being a fully developed industrial application. And the idea here is to being capable of recycling fibers, in this case, carbon fibers. The university developed a really smart way of aligning those fibers. And so with that, what we are doing is creating a tape. And this project, the project that we are currently doing, is focusing on both developing the machine, so that is more industrial, let's say, but also making sure that we find the right applications for the tape. So again, I will not cover this in a lot of detail, but more than happy to answer questions afterwards. So talking about digital and how we're using digital to really fully take advantage of the full potential of composites, we have several different big programs that we've been focusing on. So what you see on the left is our take on how we want to approach this. And probably all of us being composite engineers or researchers, we are all really familiar with the idea of design and manufacturing need to go hand in hand if you want to really fully take advantage of composites. Actually, what we would like to focus on is the full V of engineering, in this case represented as a cycle. But we want to focus on every single aspect of those, and all of these need to be happening at the same time. So what we have is, again, two different programs. One is what we call the Digital Engineering, Technology and Innovation. And as you can see there, I won't talk too much about this, but more than happy to provide more details. But basically, we're developing a number of enabling capabilities that we have considered like absolutely critical in order to be able to leverage on the digital technologies, but also really interesting proof of concept. And those are industrial applications, basically. So what we're doing is for each one of those, we're developing a demonstrator or something that really showcases what digital technologies can do for composites and some of the other technologies also. And then we have 5G encode. And what this is basically the first industrial application of 5G as a test bed in an industrial application. And again, what you can see there is basically what we're doing. This is very early stages, I guess, and the two of them are connected, but probably the most interesting one is the first one, DETI. So one of the things that we've been doing with DETI and 5G encode is to really identify what the digital system looks like. So focusing a little bit more on what are the right ways of communicating, and one of them is through quantum. So what we have done there is basically establishing the first quantum secure inter-site connectivity. So we are connecting the NCC with CFMS, which is another research center relatively close by. And the idea is that they do have quite a lot of high power computing. We can actually just unlock the secure and really almost real-time communication between the NCC and CFMS, absolutely secure, so that we essentially can take advantage of their HPC capability without necessarily investing in on-site. Probably the most interesting bit of what digital can do is, well, a number of things that have already been mentioned in the questions and answers. So we started relatively small, as you can see, with machine learning to try to identify dry fiber and pre-classify those. So this is a relatively easy entrance into machine learning, but basically what we did there was train the system with 15,000 images and then use that system to actually use to identify whether the preforms were right or wrong. Again, this is only the first step. And I will show you what we did with what we learned from this one in a couple of minutes. Another really interesting application of digital technologies is for metrology. And what you're seeing there is a fully automated drone inspection, basically. So what we're using is photogrammetry, and we have developed the system so that the drone fully automatically develops its own path to identify all of the different points that we're interested in within the tool, and fully automatically build the structure and build the surface. And obviously, we have compared this with more traditional methods that require significantly more investment, and the accuracy is within 0.2 millimeters, which is, again, for a lot of the sectors, is probably more than enough. But I think one of the really interesting applications, and going back to this idea of taking a look at the whole cycle at the same time, is for digital to really significantly accelerate certification and to improve regulation. So I already presented this in ICCM a couple of years ago, but I think it's still really, really relevant. So what you see in the current regulations is that they're really conservative. They're to some extent out of date in some cases because they don't take into account some of the more, some of the newer manufacturing processes. They're really slow to change, and in a lot of the cases, for some sectors, they don't even capture the functional requirements. So what you see, for example, in construction, at least in the UK, is that you still see something like galvanized ladders on the exteriors of buildings, which essentially prevent composites to be inapplicable. So what we really want to focus is taking full advantage of the digital technologies to, again, accelerate and update really quickly the regulations. and the certification. So again, the focus is on the diagram there. So it's concurrent engineering. Everything is happening at the same time, and you're getting all the learnings from one process to feed into the next one and also into the previous one. So we're using the digital thread, and we're building all the technologies needed for the digital thread to really gain confidence. We're obviously leveraging quite a lot on the data capturing and analytics. So we're moving, as I mentioned before, from the final inspection into in-process monitoring so that you can really analyze or update as manufactured the models, but also really interested in developing in-service monitoring, because that will actually bring back more realistic requirements, which will, in essence, improve significantly what you will need to develop in the next generation. All of these will actually bring, as far as we understand, a lot more understanding and also a lot more confidence. And one of the ideas that we really want to push with the regulators is the idea that some of the knockdown factors could actually be significantly reduced, which would make composites, again, significantly more competitive. And obviously, if you gain the confidence, the certification cycles can be significantly reduced. And this is really important in a lot of sectors, well, probably in all sectors. But if you think about aerospace and the certification cycle being so long, this is extremely useful. So this is more or less what we see as the current state of the art. So obviously you have the quality control and you have the NDT inspection and stuff like that. You do have some level of well, offline predictive manufacturing. So a lot of simulation of the manufacturing processes, and some of those are actually getting really accurate, but most of the time it's done completely offline, so in the design phase. Then you have more and more in-process inspection on top of the quality control of the final part. But what you're still missing is that lower part of the diagram. So essentially what we have done is put together some of the learnings that we got from the initial stages on the machine learning and stuff like that. And then we have come up with a relatively simple program, a relatively simple framework that we have put together for a program. And I will show you the results. But basically what we're doing is going all the way down to the in-process control. And I would explain a little bit more what I mean. So rather than having the final inspection and completely disconnected in-process inspection, mainly based for quality, and the predictive manufacturing, we've tried to put everything together. So with the part that you see in the middle and the tool, we put embedded sensors into the tool. So the in-process inspection is actually there. At the same time, we developed high fidelity simulation of the manufacturing processes. What you're seeing there is 3 different simulations based on small changes in the parameters. So things like the temperature, the resin infusion point, some of the dimensional stability of some of the laminates, etc. And then once we knew that the simulation was accurate enough, then what we used is, obviously, we correlated the simulation with what the structural simulation was telling us. But then we developed, together with the CFMS center that I mentioned before, 15,000 different simulations, changing all the parameters that were relevant in terms of having a successful part out of the infusion. With these 15,000 simulations, we managed to construct what we call a surrogate model. And that not only allows you to do in-process inspection, but also in-process on-the-fly predictive process. Basically, what you can see through the embedded sensors is where in that surface response surface you are, and you can basically understand if the process is going to be successful or not. So on top of that, we use machine learning to build an adaptive model with a really complete understanding of the process variables and the control requirements. So if you put those 2 in combination, essentially what you got is that, well, first of all, during the infusion, you know if the infusion is going to be successful or not, but also you can develop your responses, basically. So if you know for a fact that the infusion is not going to be successful, you can implement a strategy on the fly to make sure that every single part is successful. So what you end up having is a process that is completely adaptive and able to, as you can see there, able to overcome the process variation. So basically what you're getting at is not right first time, but it's right every time. So ideally what we want is to, the framework we created is quite useful. It's been really powerful and we've been implementing that in other processes. So resin infusion is to some extent relatively easy. There are other things, other processes that are slightly more complicated. So what you see there is essentially the same framework developed into the deposition of, essentially a full wing. So the picture that you see there is what we call the dry fiber pilot line. It's capable of, essentially depositing very large quantities of carbon fiber directly on the fly. So it's not a fiber placement. So what we're doing is substituting many different small tapes with a roller, basically. And what we do is we used as deposited edge inspection, but also look ahead inspection. And the idea is that if for whatever the reason, the system identifies a small variation in the deposition, it is fully capable to adapt the machine path on the fly to make sure that every single ply is deposited successfully. So, and again, this could have not been done without the work that we did in the relatively small program before. So one step before this, we have also used all of the learnings that we get from the manufacturing processes, and going back to this circular scheme or diagram that I have mentioned before, all of the knowledge that we have around manufacturing, around verification, around simulation, all of that has been fully embedded into a design tool to design and manufacture composite tanks for hydrogen. So what you see there is basically a fully automated system that allows you to successfully and reliably design composite tanks based upon the knowledge that we have in terms of design requirements, but also the manufacturing requirements. And this is essentially where we would like to get. So getting the confidence and providing the confidence to the regulators that this is actually as reliable as going through the more traditional pyramid of tests and all the time required to actually get to that. And also, as I mentioned before, ideally, as we gain the confidence, what we would like is to be able to negotiate, if that is the right word, with the regulators to actually significantly reduce the knockdown factors. That was it on my side. For those of you who are interested in automated composites manufacturing, the University of Bristol and ourselves, the National Composites Centre, we jointly had a virtual keynote presentation, a set of presentations last April. But we are having the face-to-face conference in 2022 in Bristol. So for those of you who are interested, you can contact either myself or Professor Michael Wisnum. We'll be more than happy to provide additional information on this. So that was it on my side. I wanted to provide a little bit more time for questions just in case. So thank you very much for your attention. And yeah, I'm more than happy to take the questions now.
Okay, thank you very much, Dr. Garcia. So I have one question here in the Q&A. So I'll just read out directly from the tabs. And let me rephrase this. How to obtain the recycled continuous fiber for the tape material? Is it obtained from the discarded parts or components?
Yes. Yeah, sorry, I should have mentioned that. So essentially, for this case in particular, what we're doing is we're taking a VTP from a plane, getting the fiber, chopping it down into short fibers, and then the system developed by the University of Bristol is essentially getting a really good alignment. So what you get is a tape formed with short fibers, relatively short fibers. It's definitely not continuous. But essentially what you can get is significantly improved mechanical properties when compared to randomly aligned because of this alignment of the process. And then what we're doing is essentially manufacturing stuff with AFP, with the tape that we're manufacturing.
All right, okay, very clear. And yes, I just want to let you know for the panelists, you can unmute and you can ask question directly. And for all these attendees, you can also type in the Q&A part, not in the chat, not in the Q&A. This is coming from, I think from Delft, Mohammed Nasser Saleh. So out of all the composite manufacturing techniques or processes, what would you consider the most challenging to implement in process monitoring? For instance, weaving, especially 3D weaving, can you capture through thickness defects or flaws, or is it only just so far surface in process monitoring? It's very interesting.
This is a really good question. So 3D weaving is most definitely challenging. Actually, I have to say, we as the National Composites Centre, we're not the experts in the UK in 3D weaving. Actually, AMRC, one of the other 7 centres, have a very good 3D weaving capability. But yeah, certainly 3D weaving is really, really challenging. I would say that one of the really difficult ones, at least in our experience, is anything that has to do with dry fiber and then the infusion or the RTM or any other technology that infuses the resin into the fiber. Reliably capturing what the defects are at the right level of definition is very challenging.
Hi, Enrique. This is Suresh Advani. How are you?
Hi, Suresh.
So good to see you and nice talk. I had a couple of questions. One,
sure.
Just information, which is, were you using LIMS in your infusion simulations to do the 15,000 simulations and collecting the data?
Yes, yeah, absolutely. Thank you for the reminder. I should have mentioned that, but yeah, no, absolutely. We used LIMS because it was extremely efficient in terms of setting up the 15,000 simulations. So we identified this as the best possible simulation tool. It's also, it can be really accurate if you spend the time with it. So,
right. Yeah. So the other related question, I'm curious, when you did this, getting it right every time, when you did that experiment, what were the results like? What did you find?
So what we found is that, well, as I mentioned before, the in-process monitoring of infusion, in this case, I should have said, this is actually RTM, so it's a really quick process. It is really challenging. So one of the main challenges for us was to develop a simulation that was accurate and reliable enough. But actually, one of the learnings was that machine learning is surprisingly good. I mean, what we managed to go to is through the response surface that we created, we could gather information relatively quickly and come back with almost instantaneous response, which again, coming from simulation and the way we usually do simulation, that was quite a surprise, to be honest.
That's good. So, sorry, so just to cut you, there's just one quick question, I think from Professor Sanjay Rastogi, just quick question. We have 1 minute left.
Okay, my quick question is, you mentioned about the carbon fibers that you get from the chopping from the recycle process, and then you're making them into tapes or so.
Yep.
So what is the modulus in the strength? Because the modulus in the strength is likely to drop of the carbon fibers.
Yeah, I mean, obviously you don't get the same level. I mean, you don't get the same level of mechanical properties that you can get with the pristine, virgin, continuous carbon fiber laminates. I mean, that's a given, but it is significantly closer than you might think. So it really depends on well, first of all, on the fibers that you use, of course, on the process that you use to recycle, because I mean, pyrolysis is different from some of the more, I mean, other approaches that are coming up. The length of the job fiber and also the let's say the quality of the short fiber, so the consistency of the fibers, but the mechanical properties are surprisingly good. I mean, Suresh also can probably talk about all the developments that they have done with a similar idea, or a very similar idea, I would say.
Because the composite, the main thing which would also influence is the matrix that you use for impregnation. And then they'll have the homogeneous distribution of the wetting process, etc., becomes quite a challenge.
Yeah, but the beauty of this is that because of the, I would say, really good alignment of the fibers, what you get is significantly more consistency than with anything else that I've used in terms of completely randomly oriented.
So if I may add, Sanjay, there is a material that Center for Composite Material has developed called Tough. There are SAMPE talks on it. You can go look up those talks, and they can get properties that are equivalent or better in some cases than the continuous fibers. So it's
surprising.
Yeah, so you can take a look at those papers, and all your questions about wetting, alignment, homogeneity will be addressed there.
Thank you.